Refrigeration plays a very vital role in different aspect of chemical process utilities. And when we are talking about the refrigeration aspect, then we cannot overlook the importance of refrigerants. So welcome to the new concept of this refrigerant and refrigeration. Now in this particular lecture, we are going to discuss about the brief outlay of the refrigerants. Then we will discuss about the classification of refrigerants. This inclusive of halocarbons, hydrocarbons, inorganic compounds, azeotropic mixtures, non-azeotropic mixtures. We will discuss about the prefix and coding of refrigerant. We will discuss about the isomers, and we will, apart from this, we are going to discuss about the refrigeration and its history. See, refrigeration is, as I told you, that the refrigeration is an integral part of chemical process industries, and it is clubbed under the edge of utility, because there are so many processes in which you need to have lower temperature operation, and sometimes you need to extract the excess amount of heat from any process. And this usually carried out with the help of refrigeration cycle and with the help of refrigerant. So the refrigerant, they are well known as a fluid absorbing heat during the evaporation, and which provides a cooling effect during the phase change from liquid to vapor, and are commonly used in refrigeration, air conditioning, heat pump system, and in the process system. There are a couple of examples of the refrigerants like ammonia, sometimes referred as R717, carbon dioxide referred as R744, ethyl chloride referred as R160, isobutane referred as R600A, methyl chloride R40, methylene chloride R30, and sulfur dioxide R764, and other chlorofluorocarbons. Now, since they play a very vital role, so based on the various parameters and aspects, we can classify those refrigerants or on various basis. The primary refrigerants, these can be classified into different categories, and especially the 5 categories: halocarbons, hydrocarbons, inorganic compounds, azeotropic mixtures, and non-azeotropic mixtures. So let's discuss about the halocarbons. The halocarbons contain one or more of the 3 halogens, chlorine, fluorine, and bromine, and they are widely used in refrigeration and air conditioning system as refrigerants. They are commonly known by their trade names such as Freon, Arcton, Genetron, Isotron, and Uron. In this group, the hydrocarbons consisting of chlorine, fluorine, and carbon, they have been the most commonly used refrigerants, so-called chlorofluorocarbon or CFCs. Now, the CFCs have been commonly used as a refrigerant solvent and foam blowing agents, such as most common CFCs. They are CFC 11, R11, CFC 12 or R12, CFC 113 or R113, or CFC 114 or R14. Now, CFCs are odorless and non-toxic and heavier than air, as well as the dangerous if you are not handling them properly. The inhalation of high concentration is not detectable by human senses and can prove fatal due to the oxygen exclusion caused by the CFC leakage in the enclosed arena. The combustion product of CFC includes the phosgene, hydrogen fluoride, hydrogen chloride, which are equally poisonous if they are inhaled. Now, there are some other components such as halon, carbon tetrachlorides, perfluorocarbons. The halogens are compounds consisting of bromine, fluorine, carbon, and this halon 1301 or 1211, they are used as a fire extinguishing agent, both in built-in system and in handheld portable fire extinguishers. The carbon tetrachloride CCl4, this was widely used as a raw material for many industrial uses, including the production of CFCs, and found carcinogenic, and that is why it has been discarded over the period of time. Then perfluorocarbons, PFCs, They have an extremely high effect on global climate change and very long lifetime. They have impact on the global warming. Now, second category is the hydrocarbons. Hydrocarbons or HCs, they are the compound that mainly consists of carbon and hydrogen, and these hydrocarbons includes the methane, ethane, propane, cyclopropane, butane, cyclopentane, etc. Although these hydrocarbons are highly flammable, they may offer various advantages as an alternative refrigerants because they are inexpensive to produce and they have a zero ozone depletion potential, and they have a very low global warming potential, and they possess a very low toxicity in nature. There are various types of hydrocarbons like hydrobromofluorocarbon HBFCs. They are the compounds that consist of hydrogen, bromine, fluorine and carbon. Then hydrochlorofluorocarbons HCFCs, they are compounds that consist of hydrogen, chlorine, fluorine and carbon, and they can deplete the ozone but in lesser extent than the CFCs, and they are having the potential of ranging from 0.01 to 0.1. Then hydrofluorocarbons HFCs, they are the compound that consist of hydrogen, fluorine and carbon. They can be used as the replacement of CFCs because don't contain chlorine, bromine, and they don't deplete the ozone layer, but and that their depletion potential is about to zero. Methyl bromide CH3Br, this is the compound consisting of carbon, hydrogen, bromine. It is an effective pesticide and used to fumigate soil and many agricultural products, and they have the depletion potential of 0.6. Methyl chloroform CH3Cl, this is the compound consists of carbon, hydrogen and chlorine. Methyl chloroform is used as an industrial solvent. Its ozone depletion potential is 0.11. For refrigeration application, a number of hydrocarbons such as methane R50, ethane R170, propane R290 and butane R600 and isobutane R600A that are suitable as a refrigerant. These can be used easily or frequently. There are certain inorganic compounds. Now, in spite of early invention of inorganic compound, today they are still used in many refrigeration, air conditioning and heat pump application as a refrigerant. The examples are ammonia NH3, water H2O, air, carbon dioxide, sulfur dioxide. Now, in this particular study, we have focused on three compounds of this family, that is ammonia, carbon dioxide and air. So, let us talk about the ammonia, that is R717. Ammonia is a colorless gas with a strong pungent odor which can be detected at a very low level, that is 0.05 parts per million or ppm. Liquid ammonia boils at atmospheric pressure at minus 33 degrees Celsius. Now, this particular gas is lighter than air and extremely soluble in water. Now, despite of its high thermal capability to provide cooling, it may cause several technical and health issues or problems. These may include that gaseous ammonia is extremely irritating to eyes, throat, nasal passage, skin, or exposure to the to level in the range of say 5 to 30 ppm. This reported to eye irritation. Exposure to the level of 2500 ppm causes the permanent eye damage, breathing problems or difficulties, asthmatic spasm and chest pain. Non-fatal poisoning may lead to the development of bronchitis, pneumonia and impaired lung function. Ammonia is a flammable gas and forms potential explosive mixture with air in the range of 16% to 25% ammonia in air. The ammonia vapors react with the vapors of acid like HCl to produce an irritating white smoke. Ammonia and ammonia-contaminated oil, they must be disposed of in a proper way approved by the local regulatory authorities or guidelines given by the various state boards and central boards. Although ammonia is an excellent refrigerant and indicated that these possible disadvantages can be eliminated by the proper designing of system and control of refrigeration mechanism. Carbon dioxide. It is the oldest inorganic refrigerant. It is colorless, odorless, non-toxic, non-flammable, non-explosive refrigerant and can be used in cascade refrigeration system, dry ice production and food freezing operation or application. Air. Air is generally used in aircraft air conditioning and refrigeration system. Its coefficient of performance is low because of light weight of the air system. In some of the refrigeration plant, it may be used in the quick freezing of food products. Azeotropic mixtures. An azeotropic refrigerant mixture consists of two substances and these can't be separated by usual distillation protocol. Now they are having the different properties but behaving as a single substance. So that is the quality of azeotropes. The most common azeotropic refrigerant is R502, which contains 48% of R2020 true and 51.2% of R115. Its lesser toxicity provides an opportunity to use this refrigerant in household refrigeration system and the food refrigeration industry. There are certain non-azeotropic mixtures. Now, non-azeotropic mixture is a fluid consisting of multiple components of different volatiles that when used in the refrigeration cycle change composition during the evaporation, boiling or condensation. Non-azeotropic mixture became more attractive in research and development on advanced vapor compression heat pump system. Now there are so many advantages associated with the non-azeotropic mixtures. One is that energy improvisation and saving, then the capacity control, then adoption of hardware component regarding capacity and application limits. Now widely used refrigerants such as R1, R12, R22 and R114 became most popular for the pure component of non-azeotropic mixtures. Now there are secondary refrigerants. Now secondary refrigerants, they play a role in carrying heat from an object or space being cooled to a primary refrigerant or the evaporator of a refrigeration system. During this, it has no phase change. The most common secondary refrigerant brines, which are water salt, that is the sodium chloride and calcium chloride solution, and even today they are still in use in spite of their corrosive effects. The antifreeze, which are the solution of water and ethylene glycol, propylene glycol or calcium chloride, they are widely used as the secondary refrigerants. Propylene glycol, they has the unique feature of being safe in contact with food products. Dichloromethane CH2Cl2, trichloroethylene C2HCl3, alcohol solution and acetone, they have been used in some special applications. There are various features attached or attributed while considering as a main criteria in the selection of proper secondary refrigerant. One is that the satisfactory thermal and physical properties. Second is the stability because it goes to the various cycles under the stress of pressure and temperature conditions. So, it must be stable, it should not be decomposed over the period of time, otherwise it may become a problematic approach. It must have the non-corrosiveness and non-toxicity, and above all it should be cost effective, and it must possess the usability aspect. Now, sometimes you see that there are certain prefix and the coding is there while we use any kind of refrigerant. So, prefix and decoding of refrigerant, the various refrigerants like CFCs, HCs, CFCs, HBFCs, etc., they are numbered according to a system devised. Although it may seem confusing, in fact, it provides very complex information about the molecular structure and also easily distinguishes among the various classes of chemicals. Now, prefixes. Most common refrigerant prefixes are CFCs, HCFCs, HFCs, etc. In CFCs and HFCs, the first C of the chlorine, and in all of them F for fluorine and H for hydrogen and C for carbon. The PFC is a special prefix meaning perfluorocarbon. Per means all. So, perfluorocarbon have all bond occupied by the fluorine atom. Now, here you see in this particular table that the chlorofluorocarbon, the prefix is CFC, and atoms this contain chlorine, fluorine and carbon. Then hydrochlorofluorocarbons, HCFCs, hydrogen, chlorine, fluorine and carbon. Similarly, hydrobromofluorocarbon, HBFCs, hydrogen, bromine, fluorine, carbon, and hydrofluorocarbon, HFC, hydrogen, fluorine, chlorine, hydrocarbon usually HC, hydrogen and carbon, perfluorocarbon PFC, that is the fluorine and carbon, and halon, that is represented as halon, bromine, chlorine, hydrogen, fluorine, carbon. Now, decoding the number, it helps us to provide or to find out the number of each type of atom, and the key to the code is to add 9T to the number. The result shows the number of carbon, hydrogen and fluorine atoms. For example, HCFC, that is 141B, that is 141 plus 90 is equal to 2, number of carbon, number of 3, number of hydrogen, and 1 number of hydrogen. Now, all of these chemicals are saturated so that they contain only single bonds. The number of bonds available in carbon based molecule is 2C plus 2. Thus, for HCFC 141B, which has 2 carbon atoms and there are 6 bonds. Chlorine atom occupies the bond remaining after the fluorine and hydrogen. So, HCFC 141B has 2 carbon, 3 hydrogen, 1 fluorine and 2 chlorine. So, this represents the C2H3FCl2. Now, where the HCFC designation is a good double check on the decoding containing hydrogen, chlorine, fluorine, carbon. The B at the end describes how these atoms are arranged. Different isomers contains the same atom, but they are arranged in a different fashion. Now, isomers. Now, let us talk about the isomers. The isomers of a given compound contain the same atom, but they are arranged differently and having the different properties. So, all of the compound under the discussion, they are based on the carbon chain, 1 to 3 carbon atom attached in a line of a single bond, like CCC. The naming system is based at how hydrogen, fluorine, chlorine, bromine atoms are attached to the chain. A single carbon atom can only bond with 4 other atoms in one way. So, there are no isomer of those compounds. For 2 carbon molecule, a single lowercase letter following the number designates the isomer. For 3 carbon molecule, a lowercase 2-letter code serves this purpose. Now, consider 2 C molecules like HCFC 141 or HCFC 141A and HCFC 141B, in which all have the same atoms, 2 carbon, 3 hydrogen, 1 fluorine and 2 chlorine, but they are organized differently, and that is the beauty of isomers. Now, to determine the latter, the atomic weight of the atom bonded to each of the carbon atom, the arrangement that most evenly distributes the atomic weights has no letter. Now, the next most even distribution is A, isomer, and next is B, until no more isomers are possible. Common way of writing isomer structure is to group atom according to the carbon atom with which they bond. Thus, the isomer of HCFC141R, like HCFC141 CHFCl, then CH2Cl, atomic weight on the 2C is 37.5 and 55.5. Similarly, if we talk about the HCFC 141A, so the CHCl2 CH2F, the atomic weight on the 2C is 21 and 72. And similarly, we can describe this HCFC 141B, that is CFCl2 CH2, and atomic weights on these are 3 and 90. Now, the question arises that we are having the enormous choices of refrigerant, then what should be the criteria for the selection of proper refrigerant to the system? Now, there are many criteria for the selection of the refrigerant for the use in the refrigeration or heat pump system. The refrigerants are expected to meet the different conditions, like they must have ozone and environmental friendly, they must have with a lower boiling temperature, they must have a low volume of flow rate per unit capacity, the vaporization pressure should be lower than the atmospheric pressure, and they must possess the high heat of vaporization. Apart from this, they must have the property of non-corrosiveness and non-toxicity. They must have non-acidic in case of a mixture with water or air, because it's very common that they will be in contact with this water and air. Similarly, they must be chemically stable, as I told you that they will be under the stress of pressure and temperature, so they should not get decomposed. The suitable thermal and physical properties should be there, and they should be easily detectable in case of any leakage, and they must have a low cost. Obviously, it is desirable. They must have non-flammable and non-explosiveness, and above all, they must have non-corrosiveness and non-toxicity. Now, let us talk about, because we have discussed the fluid in question for the refrigeration purpose. Now, let us discuss about the refrigeration, because refrigeration is the operation. So, the refrigeration is the process of removing the heat from the matter, which may be a solid, a liquid or a gas. Removing heat from the matter cools it or lowers its temperature, and that is quite common phenomena in all kind of chemical engineering operations. The lowering the temperature in the older method may be accomplished by the rapid expansion of the gases under the reduced pressure. Thus, if you see that the cooling may be brought about a compressing air, removing the excess heat, producing in compressing it, and then permitting it to expand. This is the common refrigeration cycle. Now, the lowering the temperature is also produced by adding certain salts such as sodium nitrate, sodium thiosulfate, sodium sulfite to water, and there are two common methods of refrigeration. One is the natural and second one is the mechanical. Now, in natural refrigeration, ice has been used as a refrigeration since ancient time, and still it is being used. In this process, forced circulation of air passes around the blocks of ice like this. These are the blocks of ice, and forced air is passed through that. As a result, some of the heat of the air is transferred to the ice, thus cooling of the air, and particularly for the air conditioning applications. Now, in mechanical refrigeration, a refrigerant is a substance capable of transferring heat, and that is that it absorbs at low temperatures and pressure to a condensing media. Now, in this region of transfer, the refrigerant is at higher temperature and pressure. By means of expansion, compression and cooling medium such as air or water, the refrigerant removes heat from a substance and transfer it to a cooling media. Now let's talk about the refrigeration system, the main refrigeration system and cycle. The main goal of refrigeration system, which performs the reverse effect of heat engine, is to remove the heat from a low level temperature medium, that is the heat source, to transfer this heat to a higher level temperature medium, and that is called the heat sink. Now in this system, the refrigerant is used to transfer the heat. This is quite simple phenomena. The refrigerant absorbs heat, and that is temperature is lower than the source. Hence, increase in temperature during the process to a temperature higher than the heat sink's temperature. Now here this represents the pictorial diagram. Now this is the heat sink. This is the system refrigeration, and this is the heat source. Now TL, this is the absolute temperature of the source, and which is maintained at the lower temperature, and you need to extract the QL amount of heat from this heat source through this system by incorporating the W amount of the work, and you need to discharge this QH amount of heat to the heat sinks, which is maintained that at TH. Now here the TH is greater than TL. Now for centuries, because this is a very common phenomena, and we are following this phenomena for ages, so it's good enough to have a brief history discussion about the refrigeration. Now for centuries, people have known that the evaporation of water produces a cooling effect. At least as early as the 2nd century, evaporation was used in Egypt to chill the jars of water, and it was employed in ancient India to make ice. Now depending on this particular phenomena, in 1755 a Scottish physician, William Cullen, obtained sufficiently low temperature for ice making. In 1834, Jacob Perkins, an American residing in England, constructed and patented a vapor compression machine with the compressor, a condenser and an evaporator. Now new substances like ammonia and carbon dioxide, which were more suitable than water and ether, were made available by Faraday and others, and they demonstrated that these substances could be liquefied. The theoretical background required for the mechanical refrigeration was provided by Rumford and Davy, who had explained the nature of heat by Kelvin, Joule and Rankine, and continuing work by Sadi Carnot in formulation of Science of Thermodynamics in 1946. The refrigeration machine was appeared between 1850 and 1880 and classified according to the refrigerants. Dr. John Gorey, an American, developed a real commercial cold air machine and patented in 1951, and the refrigerating machine using cold air as a refrigerant were divided into two types, closed cycle and open cycle. In Europe, Dr. Alexander C. Kirk in 1862 and Franz Windhausen in 1870, they invented a closed cycle refrigeration machine and patented. The open cycle refrigeration machine was theoretically outlined by Kelvin and Rankine in early 1850, and it was invented by Frenchman Paul Giffard in 1837 and by Joseph C. J. Coleman and James Bell in Britain in 1877. In 1860, a French engineer, Ferdinand P. Edmond Carr, invented an intermittent crude ammonia absorption apparatus based on the chemical affinity of ammonia and water, which produced ice on limited scale. A comparatively large scale ice making absorption unit was constructed in 1878 by F. Windhausen, and it operated continuously by drawing water from sulfuric acid with additional heat to increase the affinity. The vapor compression machine was invented and patented by an American professor, Alexander Twining, in 1853. He established an ice production plant using the system in Cleveland, Ohio, and could produce close to a ton per day. In France, Carre developed and installed an ether compression machine, and Charles Tellier constructed a plant using methyl ether as a refrigerant. Linde, common protocol being used in various kind of vapor compression cycle. He had paved the way of great improvement in refrigeration by demonstrating how its thermodynamic efficiency could be calculated and increased. The inventor of compression machine also experimented with ammonia, which became the most popular refrigerant and was used widely for many years. In 1860, the Tellier developed an ammonia compression machine. The ammonia had thermodynamic advantage. The pressure it required was easy to produce, and machine which used it could be smaller in size. In late 1860, the P.H. Vanderwide of Philadelphia got a patent for a compression unit which featured a refrigerant composed of petroleum product. In 1875, R.P. Pictet at University of Geneva introduced a compression machine that used a sulfuric acid. In 1866, TSC Law, an American developed refrigerating equipment that used the carbon dioxide. Between 1880 and 1890, ammonia-based compression cycles, the installation became more and more common. By 1890, the mechanical refrigeration had proved to be both practical and economical for the food refrigeration industry. Now, study technical progress in the field of mechanical refrigeration, they marked effect in 1890. The revolutionary changes were not the rule, but many improvements were made in several countries in the design and construction of refrigerating units as well as in their basic component, compressor and condenser evaporators. So, in this particular lecture, we discussed about the different kind of refrigerant, classification of those refrigerant. We discussed about the basic theory of refrigeration. We had a discussion about the history of refrigeration, and if you wish to have a further reading, then you can have a look of this particular reference. Thank you very much.